Hi, my name is Elena Statue, and I'm a student at Case Western Reserve University in the Engineering 225 class. And today I will be explaining the concept of entropy, related equations, and examples. So to start, usually at first you learn the first law of thermodynamics, which describes the conservation of energy. The energy into a system is equal to the energy out from a system. But this doesn't explain everything, because, for instance, with this coffee cup, with the coffee being at a higher temperature than the surroundings, it makes sense that the heat transfer would be from the hot substance to the colder substance, so from the coffee to the surroundings. But there never is a case where the surroundings put energy into the coffee cup to make it warmer. So this means that the process only proceeds in one direction, and this is the property known as entropy. And German physicist R.J.E. Clausius came up with an equation to describe entropy, and this is in its differential form. So this equation represents the differential of entropy, which is equal to the differential of the heat transfer over a temperature, and this is for an internally reversible system. And internally reversible means that no irreversibilities occur within the boundaries of the system that's defined, and these irreversibilities are factors that will affect whether the process is reversible, so it can go in a forward reaction or in a reverse reaction, or if it just proceeds in one direction, like I had explained earlier with the coffee cup and the surrounding atmosphere. So, to give a more specific example, I will have oxygen molecules traveling through a pipe, and these are the oxygen molecules, and the hallway will represent the pipe. So, the oxygen molecules will be traveling through the pipe. From the inlet to the outlet. And they're banging against the wall, they're banging against each other, lots of motion until they approach the outlet. Alright, so we can examine the entropy changes in the system. We can first examine the entropy change associated with the oxygen molecules. And this equation here describes the entropy change. This is for an ideal gas, in which we are considering oxygen as an ideal gas. So it's the entropy change from state 1 to state 2. State 2 being the outlet, or when the oxygens leave the pipe, and state 1 being the inlet when the oxygens enter the pipe. And there are different equations you can use. This is one of them, which shows the temperature and the pressure changes as the oxygen molecules go through the pipe. But another case can be when the temperature and the volume changes. But in this case, since the volume is constant, since it's going through a pipe, we're using this particular equation, which has the specific heat, the temperatures, the ideal gas constant, and the pressures. We can also examine the entropy change associated with the surroundings, but to do that, you first have this general equation, which is just, as what you had seen before, is the general definition of entropy. Delta S equals the change in heat transfer over a constant temperature. But we don't know what delta Q is, and to find delta Q, we go back to the first law, and this is a representation of the first law for an open system, which means there's mass flow. And in this case, there was, because the oxygen molecules represent the mass flow entering and exiting the pipe. There's no work in or work out, so this part cancels. But you've got the change in enthalpy from state 1 to state 2, the mass flow, and overall this delta Q, which is Q in minus Q out. And then taking that factor, you can put that into the equation. The T0 is the overall constant temperature of the surroundings, because this represents an isothermal heat transfer process. And because the surroundings are so large, the temperature is probably going to change negligibly. So overall, there is one constant temperature for the surroundings. And then you can examine the overall system, which is the oxygen molecules through the pipe and the surroundings, and add it all together. So this is the total entropy. This is the entropy of the system, oxygen molecules, entropy of the surroundings, and then the total entropy. And the total entropy can tell you if the process is reversible, irreversible, or impossible. If it's greater than 0, it's an irreversible process. It only proceeds in one direction. Reversible means it can proceed in both directions, and impossible means It just can't happen. So in this particular case, by calculating the entropy and the enthalpy losses, you can determine what kind of system you need and what driving forces you need to make sure that this gas, like the oxygen, goes through the pipe at a certain distance and will exit where you need it to. And that is a quick explanation of entropy, and that's it. Hope you enjoyed the show.